And lattice energy is defined as the amount of energy that's needed to break two ions apart that are in an ionic compound. So if I have sodium ions bonded to chlorine ions, how much energy do I need to separate those ions? It's also the amount of energy that's released when those two ions come together to form an ionic bond. It's similar to bond dissociation energy, which we talked about in chapter 9. It's just that bond dissociation energy is for covalent bonds, right? How much energy we need to break the bond versus and how much energy is released when we form it, versus lattice energy, which is for ions. So it's kind of the ionic bond version of bond dissociation energy. So the amount of energy needed to, we could say, break an ionic bond. The official definition is more about to free an ion from an ionic solid, but essentially it comes down to we have an ionic bond and we're removing an ion from that, so we're breaking our ionic bond. And we can just think about it that way, and that'll work for us. So the amount of energy needed to break an ionic bond. So if I have sodium chloride and I want to separate those into sodium ions plus chloride ions, that's going to take energy to do that. That energy is my lattice energy. So we have to put energy into breaking that. Of course, we can then put the arrow in the other direction, right? It's going to be the amount of energy released when we form that ionic bond. So if it's going to be positive in the forward direction, we're going to think about it as that, right? The amount of energy that we need. But if we were to turn that arrow around, it's going to be the same amount of energy, but we're releasing it when we're forming that bond. So it is fine to think about it in that direction. The magnitude of the energy is going to be the same. It's just the sign on that value is going to be different. Am I putting energy into it, or am I getting energy out of it? So as you would imagine, not all ionic compounds have the same lattice energy. And whether it's a big value or a small value, it's generally related to two things: the size of those ions and then also the charge on those ions. And there is a formula that goes with this. I'm not going to give it to us. We don't really need it. We can just remember that the bigger the charge, the more attraction they are, so the more energy we need to separate them. And then as far as size goes, when we're talking about lattice energy, I could like draw a picture here. So my nucleus, again, totally not to scale. And I have an electron. And then I have another atom. Again, totally not to scale. It's its electron. And what's happening, I'm actually going to move that electron out of the way a little bit, is that the electron of one atom, right? We can think of this as being attracted to the neighboring nucleus. When we're talking about ionization energy and electron affinity energy, we're talking about an atom's electron being attracted to its nucleus. Here we're talking about one being attracted to another. This one is attracted to this. So the smaller the atoms are, the closer they can get to each other, the more attracted the electron of one is to the nucleus of the other. So smaller atoms are going to have higher lattice energies because they can just get closer, right? That attraction is greater. It's held more tightly, so it's going to take more energy to separate them. So kind of our two trends: bigger charge. So, and by bigger charge, I just mean like a +2 is larger than a +1. A -2 is also bigger than a -1. So I'm talking about the magnitude, not the sign of that charge. So maybe we should say the larger the charge. I don't know what the right wording is. The larger the charge, the more attraction between the ions. So larger lattice energy, right? If there's more attraction, it's going to take more effort, right? More energy to break them apart. If there's more attraction, we're going to release more energy when we form it. So larger the charge, The more attraction between the ions, the larger the lattice energy. And then size, the smaller the radius, just so you know, I'm not talking about mass, or when I just say larger, I'm not talking charge. So the smaller the radius of the ion, the closer they can get to each other. The larger the lattice energy. So let's look at some examples. So we're going to rank the following in order of increasing lattice energy. So again, when I say increasing, we want the smallest one first going to the largest. So let's do sodium chloride, lithium chloride, cesium chloride. So the first thing I would do is I would look to see kind of what the difference is between these. So they all have chlorine in them, or chloride ions in them, so I can kind of ignore that part. So the part that's different, sodium, lithium, cesium. And then I'm like, okay, am I going to use the charge trend or the size trend? All three of those have the same charge, right? Sodium with a +1 charge, lithium with a +1 charge, and cesium with a +1 charge. So I can't differentiate these based on charge. I'm going to have to differentiate these based on their size. So we have smaller radius, larger lattice energy. So lattice energy increases inversely to the size of that atom. So if I want to start with the smallest lattice energy, I'm actually going to start with the largest of those ions. So just using the trends in our periodic table, remember as we go down a group, more and more shells are occupied with electrons, right? As our value for n gets bigger, its extension into space gets larger. So these are all in the same group. I can just take the one that's further down, right? It has more occupied shells. It's going to be a larger atom. So looking at our periodic table, cesium chloride is our biggest, right? Cesium's bigger. So it's going to have my smallest lattice energy. Sodium chloride is next. And then lithium, of those three, sodium, lithium, and cesium ions, is our smallest. So it's actually going to physically be able to get closer to chloride ions. It's going to have the largest lattice energy. So we're using our size trend here, right? Bigger ions have smaller lattice energies. U is the abbreviation for lattice energy. I don't know if I told you that. You don't necessarily need it, but when I start abbreviating on you, it's good to know what I'm talking about. So bigger, I guess we should actually say bigger what? Bigger ions have smaller lattice energies. Smaller ions have larger lattice energies. So that was our trend for this example. Let's do another one. So that was part A. Part B, magnesium bromide, sodium bromide, and aluminum bromide. So I'm going to do the same thing. I'm going to look to see what the difference is between them. I'm using bromide for all of them. I don't have to use the same anion for all of them. The examples I picked just happen to work out that way. But generally, the first thing you want to do is determine, are you basing it on size or basing it on charge? Since my bromide is the same in all of them, I'm just going to ignore that. So what I'm looking at is I have magnesium with a +2 charge, right, and 2 Br minuses. I have sodium with a +1 charge, and then aluminum with a 3+ charge. Oop, and 3. If aluminum is +3 and bromide is -1, I need 3 bromides for every 1 aluminum. Sorry about that. Oh my goodness. It's early, guys. Bromide is -1, sodium is +1, so 1 of each. Sorry. Now that we have basic chemistry worked out, we can actually answer a question. So bromide's not changing, it's a -1 charge in all of them. The part that's changing is my cation. So I have magnesium with a +2, sodium with a +1, and aluminum with a +3. So we're going to use our charge trend on this one, right? The larger the charge, the more attraction between ions, so the larger my lattice energy. So since we want to go increasing, we want the smallest one first. So sodium bromide is going to have a smaller lattice energy than magnesium bromide, which will have a smaller lattice energy than aluminum bromide. So our size trend on this, or sorry, our charge trend, right? The larger the charge, the larger the lattice energy. If you have one where we're mixing charge, like you have something that has a bigger charge, but it's actually a larger atom, our charge is actually going to win. Now, if they're extremely different, then honestly, I would have to look up the values, but if they're pretty close, charge is going to win. I won't give you anything that's really far away. In fact, I usually stick within a trend, but I know there's a homework question where they mix them. So if given, and I'll give you an example here. If given a couple compounds, 2 compounds, and one is smaller, but the other has the larger charge, charge wins. So the one with the bigger charge is going to have the higher lattice energy. So if I was to compare magnesium bromide versus lithium bromide. So I'm keeping bromide the same again, just to not throw too many variables in the mix. But I have magnesium, which has a +2 charge, and lithium with a +1 charge. Lithium, however, its outermost shell is n = 2, right? It only has energy, electrons in the second energy level. Well, it has them in the first 2, but its highest is the second. And then magnesium is in our third energy level. So it's actually bigger than lithium, but it has the larger charge. Magnesium bromide is going to have the larger lattice energy. And I actually looked up the numbers just to give you, I don't know why I'm drawing mu instead of u. Habit, I guess. U. My lattice energy for magnesium bromide, 2,440 kilojoules per mole. And then for lithium bromide, it is 807 kilojoules per mole. So even though lithium's smaller than magnesium, magnesium has the bigger charge, and charge is going to win. So the magnesium bromide is going to have the larger lattice energy.